Okay, so this one says the base of a solid is the region in the first quadrant bounded by this line and the coordinate axis. What's the volume of the solid if every slice cross-section is perpendicular to the x-axis is a semicircle? Well, if you think about it, that's exactly this situation right here, where we're going to have a region. Now, it said perpendicular to the x-axis. These would be perpendicular to the y-axis. But the slices here are going to be semicircles. So what that means is something like this. So we've got a solid created with these semicircles coming up off the page. But if you look at that, you can see that the strips, that is the diameter of the semicircle. So the strip is the diameter of the semicircle. So all we need to do is, going back to this, is put that area right in there. We just need to do the strip, and that's our diameter, and then put that into our interval. So when we come back to this problem here, all we need to do is graph this thing. Now this was a no calculator, you're right. So all right, so we need to be able to graph this. Now you could get the y by itself, or there's a pretty quick way to graph these. Remember from algebra where you can just do intercepts, put a 0 in for x, put a 0 in for x, you get y is 2. Put a 0 in for y, you get x is 4. And so you could draw this line pretty quickly by doing that. And it says it's in the first quadrant. It's bounded by the coordinate axis, I guess is what it says. So here's our region. And it says the slices are perpendicular to the x-axis, so they're going to be this way. And that is, imagine a semicircle coming up off the page like so. That's your diameter right there. So when we write our strip, it's going to be the top y value, which is the line. Oh, we had to solve for y anyway. So we take away x, so we get 2y equals negative x plus 4. We divide by 2, we get negative 1/2 x plus 2. So it's going to be the top y value, which is the line, negative 1/2 x plus 2, minus the bottom y value, which is 0. And so there's our diameter of our semicircle. So it's going to be 1/8 pi times our diameter squared dx, and our strips go from 0 to 4. Now, at our quiz next week, we just type that in. Now, the other option you have is you could do half of that diameter to get the radius, right? If you wanted to do that, you could say, okay, that strip is the diameter of the semicircle, so the radius of the semicircle is half that. And then you could do 1/2 pi r squared for your semicircle if you want. So it would be 1/2 pi and then this squared. That would also work. Either way. Okay? So you just have to decide which of these equations you'd rather use for a semicircle. Okay? All right. And now, because it is a no calculator one, we'd have to go through some of this work. So we have to FOIL that out, which would be 1/4 x squared. Again, you can't distribute that square, right? It's got to be FOIL. So if you take 2 times negative 1/2 x, that'd be negative 1x. That's an outer and an inner, so you'd have negative 1x, negative 1x, right? So that'd be negative 2x. And then last times last would be plus 4. Now the 1/8 pi is out there, but I'll bring that in here later. Now I got to do my antiderivative. So raise that up to a 3, divide by 3, that'd be 1/12 x cubed. Raise that up to a 2, divide by 2, that'd be minus x squared. Antiderivative of 4, 4x. And I've got to do that from 0 to 4. And I got the 1/8 pi that I have to not forget about, and I could do that at the end. So I put my 4 in here, I get 64. 4 cubed is 64 over 12. Minus 4 squared is 16. Plus 4 times 4 is 16. Oh, that's nice. And then minus, I put 0 in, is 0 for all that. That's nice. Oh, so that wasn't bad at all. So now I get 64/12, and I got to take that times pi over 8. The 8 cancels the 64. 8 pi over 12 reduces to 2 pi over 3. So, not too bad. But, you know, we were talking about on the final, 28 questions, 55 minutes. That's about 2 minutes per question. That's a little longer than 2 minutes, probably. Some of them will be. Hopefully some of them are shorter than 2 minutes, right? And maybe they'll balance out. But that's one that had a little more way to go. But it's a good review. That'd be one very much like what could be on our quiz. It'd be just like that, where it's described just like that. You'll have to be able to sketch the region. Now you'll get to have a calculator, so that'll help you if you're not sure on the graph or whatever. But you're going to sketch the region, set up your integral, and go from there. Now, I'm not going to grade you on whether you wrote the D out here separately or whatever. You're graded on what your integral is. I think it's helpful to write out what big R or little r or D or whatever the things are. But region, integral, and then you're going to type in your calculator to get the answer. Okay? All right, so that's an example of a volume on a base. The only thing that would be different is if they said instead of the slices being semicircles, they were squares. Well, the strip is one side of the square. So you do the strip, put that formula into the integral. It's equal out of a triangle, do the strip, put that into your integral. Same thing. Okay? Yeah. Yes. Now, let's talk about that because I have seen those come up quite a bit. Well, you know it's an upside down parabola. I think I would plot a point or two. Actually, what I think, for example, put a 0 in. Finding the vertex is nice. That's not a bad thought. Do y prime and see when it's 0 because that'll be the vertex when the slope is 0. That's not a bad thought. Here's the other thing you can do is see where this crosses the x-axis, which is when y is 0. So if you just solve this for 0, you factor out an x, you get, well, when x is 0 and when x is 2. Oh, if it crosses at 0 and 2, then the vertex has to be halfway in between at 1, right? So what you have is an upside down parabola. It crosses at 0 and at 2, so the vertex has to be up here at 1. So there would be all those kind of little hints that you would use to help you do that. So then when you put a 1 in here, you get 2 minus 1, which is 1, so you know that's the point 0, 1. So yeah, to answer your question, those are kind of things that do come up in the no calculator that you got to kind of try to do. Of all the 4 sections of the test, the 2 no calculator ones, and especially the multiple choice one, is where you really have to know your algebra, your trig, all this, the graphing. The free response, not as much. The free response no calculator ones, a lot of times they have pictures drawn for you. There isn't as much where they're quizzing you on your prerequisite techniques, your previous calc classes, but it really comes up a lot in this section, which is one of the reasons I always think this is one of the harder sections, it seems like. But anyway, now you're going to revolve that around the x-axis, so that's just a circle, no empty space kind of thing. Go from there. So it is something squared, isn't it? Yeah, and you do have to do some antiderivative stuff. Yeah. All right. So I'll let you. You can check your answers on that one if you finish it out and so forth. But that's good review too. All right. Let's look at. Here's what I'd like to do right now is look at. Let's see. Yeah, this problem right here. Gosh, this is so slow. Okay, that was bad. It's not what I was trying to do. All right. So what I would like you to do is in your notebook somewhere, I would like you to do this problem. Okay, the top line here is the region. So the region bounded by y equals square root of x equals 1, x equals 4, and y equals 0. And we want to revolve that about x equals 5. Now, I'm probably not going to give you time to finish the whole thing, but up until you run into issues or whatever. So I want you to draw the region and then think about what you would have to do to start setting this one up. And if you can see it, go ahead and go as far as you can until I interrupt you. This will be calculated. This would be calculated. Yeah. This we're kind of reviewing for our quiz for next week right now. So we'll get to use our calculation. Now, with that said, on the exam, this graph should be easy enough. Everybody should be able to do it without a calculator. Okay, does everybody agree this is a region?
Yeah.
Square root of x, top half of a parabola. Okay, say that again. Don't we have to split it into two pieces? Now, okay, let's back up a minute. First of all, we're revolving this region, right? So we're talking about one of these two situations. Now, what's the difference between these two? Solid slices, no empty space. One has empty space. Does this have empty space?
Yes.
This has empty space. So we need an outer radius and an inner radius, right? We need a big R and a little r. So you need to draw in two strips. Now, what direction are they going to be? They have to be horizontal, because one of the rules is when you have a vertical axis of revolution, your slices have to be perpendicular to that. Now, I've got another thing here I can show you to review this that we're going to be getting into today. But if I look at, whoops, wrong thing. If I look at disc washer, if I have an axis of revolution that's here, my slices have to be this way. So the strips have to be perpendicular to the axis of revolution. Okay? Have to be. So I have to have horizontal strips here. I have no choice. Now, when I go to draw those, now, radius always comes from the center. What's the center? The axis of revolution. Because you're revolving around the axis of revolution, it's right in the center, and that's the 5. So your strip, so your outer radius has to go from the center out to the edge of the region. And the inner radius has to go from the center to the inner part of the region. But what happens right here at 1? They don't touch at the same place. Remember, we said that. Your strips have to always touch the same thing on the right and the left. Up here, when I draw my outer radius, it stops at the parabola. Here, it stops right there. And now my inner radius is the same, but that doesn't matter. So you have got to split this into 2 parts. This would be one of the tricky ones. Now, I'm doing this problem for a reason, because the new thing we're going to learn today, I told you we're going to learn an alternate method. So the alternate method, there are times where it's easier to use this alternate method. Now, on the AP test, probably not going to have to use the alternate method. Most of the time they make it work out pretty nice, so you probably don't use it. Okay? Now on our quiz, I'm probably going to let you choose. And probably there's going to be one, at least one would be quite a bit easier to use this alternate method we're going to learn today. Okay? All right. So, let's do it here. So that's the first part. I'm not sure all of you, very many of you even, were seeing that right now. We haven't done that many where we had to do that, right? Now, we did have some of those when we were doing areas, right? When we went to do areas, if the strips didn't touch the same thing, we had to split it into 2 or 3 or however many. All right, so we're going to have set up 2 integrals. So the first one, what's big R? The top one. Let's do the top one. The top one. That'll be 5. Yeah, it's right minus left, right? So it's 5 minus that x coordinate, which means we got to solve for x. So we get x equals y squared. So it's going to be 5 minus y squared. And little r is going to be 5 minus 4, which is just 1. Okay? So our integral will be pi on the outside. Then it'll be big R squared minus little r squared. And those strips on the top part go from where to where? 1 to 2. That'd be this right here. So those strips fill the space from 1 up here to that point, which is the point 4, 2. So from 1 to 2. Okay? The bottom section, big R, is what? 5 minus 1, which is 4. And little r is 5 minus 4, which is just 1. So this one is just going to be pi on the outside, big R squared, 4 squared, minus 1 squared, dy, from 0 to 1. And then we're going to add those up. So go ahead and do it. Let's get your calculators out and let's do it, because we're going to do this one here in a minute with our alternate form that we're going to learn today. You'll see how much easier it is. So let's take this integral and add it to this integral. Anybody got that one yet? Both of them. Just do both of them and add them together. 320, when you add them together, 328 pi over 15. Okay. 328 pi over 15. Sounds good. If we got a couple people getting it, we got it. Okay, so this could very easily be on the quiz next week. Okay. Now, in the homework today, we're going to do this alternate method, and so in the homework, they're going to require you to do them all with this alternate method. Now, what I like to do is do them both ways. Number one, it's good practice for the slice ones, and then you can compare it to your answer for the shell method. And I've even had people on the quiz do them both ways, right? If there's some of them, these revolving ones where you could do both methods, do them both and see if you get the same answer. You know, that's totally up to you if you want to do that or not. There's probably going to be at least one on the quiz where it's much, much easier to do it one way over the other. Well, this is going to be an example of that. It's going to be much easier to do that. All right. So here in a minute, we're going to do that same exact problem, okay, with this new alternate method. But first, we got to learn this new alternate method. So here's what it is. We're going to take and look at our volume problem in a different way. So let's imagine the lemon. So what we did is we took 6 slices so thick, and we cut them into 6 perfectly equal slices, right? Most of you did. And then we said, let's add up the volume of those 6 slices. And that should be the volume of the whole lemon, right? And so what we did is we said the integral will do the adding for us, and the width, eventually we want to make them paper thin, right? So that the width will turn into like the dx, but we'll do the volume of the slices added together. Okay, what about doing that same approach but doing it this way? Instead of slicing the lemon, what if we skinned the lemon? You know what I mean? Like peeled the lemon, if you will. So you took a peel like so thick of the lemon, like kind of like peeling an orange, right? The skin off of an orange. And then, so you peeled off a layer, and then peeled off another layer, and then peeled off another layer, and peeled off another layer, right? Now, if it's a perfectly kind of symmetrical thing, which we get when we revolve these things, right? Each of those would have a volume. You know, imagine they were, so thick. With onions, there you go, like an onion. There you go, peeling an onion. Oh yeah, that would be fun. Yeah, that would be good. And so that's the idea. And then use the integral again to add up the volume of all the layers. So instead of slices, it would be layers. Okay, now for some reason they call them shells. I guess there's the old shell game, the old game where, well, the shell game's like moving around. I'm not sure where shells come from. I always think of it as the old, like, you ever done that where you give somebody a present in a box and they open up the box and then there's another box? And then they open up that box and there's another box. And then there's another box inside, another box until, they think it's this great big present and it ends up being this tiny little present. Or maybe you're going to give somebody an X box and so you give them a box with just an X on it. No one would ever do that. We did that to Ryan when we wanted an X box really bad. We gave him an empty box with an X on it. So that was his. We told him that was his Xbox, and he started crying. No, that's not true. But anyway, Merry Christmas, Merry Great Parenting 101. All right, but anyway, the idea is that you would have these layers around there. Now, again, it's typical of the shell method, so you think of shells around or whatever. But it would be something like this. The shape of those would be something like this. Okay? Cylindrical shaped things. Now the blue, we're talking about the solid now, right? We're talking about the volume of the solid. So what would be the volume of a shape like this? This is what we're saying. Now what you notice though, it's going to be kind of that donut thing again. What you notice though is the strip, the thing that's going to get really, really thin. Just like here, this is going to get really, really thin as the slices get thinner. The strip is opposite. It's parallel to the axis of revolution. Now, the advantage to that is if you get a problem where it's hard to do horizontal strips because you have to solve for x, vertical strips would be better. Well, that's why this is a good alternate. Because, so this is the thing you always got to think about. So if I've got a vertical axis revolution, if I want to do slices, I have to do horizontal strips. if I want to do this new method, they're parallel. When I'm thinking of wrapping or doing layers, we're thinking about the strip wrapping around the axis of revolution. And so the rectangle, the strip, is going to be parallel to the axis of revolution. So what we need to do then is we need to think of this shape and find out what the volume of this is, because you're going to have layer inside of layer inside of layer inside of layer. The integral will add up those layers. But we need the volume of that thing right there. Now we'll get back to that in a minute. Let me show you. I've got a picture of one here. Let me reset that. So if we thought about taking this region, kind of like the one we were just doing, and revolving it around this axis of revolution, okay, we can see, I think I've got a little better picture than this one. Okay, so I'm going to take this blue region, I'm going to revolve it around here, and then the strip would be parallel. It would look something like this. Okay, so here's the solid, and then inside of here would be one of these layers. Okay, and if you see all the different layers, or if you kind of sweep the layers through there, okay, as opposed to slicing it, no, the slices would go this way, wouldn't it? So the slices would be like donuts if you sliced it this way and added up all the slices. Here we're talking about these shells. All right, so back to our calculation. So what we need to do is we need to think of what would be the volume of one of these cylinder-shaped shells. Now I need to label a couple things here, so let's call this an H. Let's call this the height of our strip. Here's our strip right here. It's kind of like what we just saw in the red a minute ago. I just kind of copied this. Now we're just going to do this together. You're never going to have to do this after we do it here. We're going to develop the formula right now, okay? So if you, how much of this you want to write down, it's kind of up to you. But what we're going to do is we're going to develop the formula for the volume of that, of the solid in that thing there. Now you, Kelsey, you said big R minus little r. So basically it's a cylinder. So it'd be like the outer cylinder minus the inner cylinder. Is that what would happen here? Like if we assume this was all solid all the way through, then it would just be a cylinder. But then we got this empty space in there, so we got to subtract that out, right? So it'd be the outer cylinder volume minus the inner cylinder volume. So what's the volume of a cylinder? Pi r squared h, but it's going to be pi big R squared h minus pi little r squared h, something like that, right? Now, so we can see big R and little r be our outer radius and inner radius. The width we need to call something here, because what we're going to do, remember, these layers are going to get, we're going to let that get thinner and thinner and thinner. So what would be a good thing to call this width here? Delta x, right? That's going to turn into the dx when we let that get really, really small. Okay? Now, the problem is, when that gets really, really small, what happens to big R and little r? They become the same thing, right? So what we need to do is we need to distinguish, and somehow we need to get delta x into this equation, right? We need to get somehow get delta x into our equation so it can turn into our dx and be part of our integral. So here's what I'm going to do. Well, yeah, number one, let's do that first. Yeah, let's take out a pi h, and then that'd be big R squared minus little r squared, so I can do that. So what I need to do is I need to write down what big R and little r would be using delta x. So I need to introduce a new variable. I'm going to call that p. Now p is going to be this distance right here. P is going to be from the center to the halfway point of the strip. Right? Now, P, when that strip gets narrower, 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 P is going to end up being like the radius, right? So P is going to be defined to be from the center out to the halfway point of the strip. So what would be big R then in terms of P? Well, let's use P though. What's big R? Big R has got to go from the center all the way to the outer edge. And remember, the width is delta x. And remember, this is half. I don't want little r in here. P plus 1/2. I don't want little r in there. I just want delta x. I want P and delta. Okay, remember, P was defined to go halfway point of the strip. So big R's got to go all the way to the edge. So it's half a width, right? So it's P plus half a width. That's what I want. P plus 1/2 delta x. That's big R. There you go. And little r would be P minus 1/2 delta x. What this is going to do is now I'm going to substitute those into my equation, and I can get big R and little r out of there because they're going to become the same anyway. So that's what P happens to P, and then delta x is going to disappear and just turn into the dx, right? So this is what I'm going to want to have. So now my volume. Now I got to write my volume equation, and then I'll stick my integral on it to add up all these layers. This is just one layer. My integral will add up all the layers. Okay, so I got pi h factored out, and then big R squared. So that's going to be P plus 1/2 delta x quantity squared minus, and then little r, so that's P minus 1/2 delta x quantity squared. Make sense? So what I'm finding is the volume of this layer, which we got by doing outer cylinder minus inner cylinder. Okay, that's where that equation came from. We introduced this thing called P, which is kind of like the radius, and delta x, because we need to get that involved, because we needed something to disappear when we do an infinite number of these layers. Okay, so I think I got everything I need. Now we're just going to FOIL that out, see what happens. So now we just had some practice on this. We'll FOIL this. This would be P squared. Outers and inners, so I'd have 1/2 P delta x for an outer and 1/2 P delta x for an inner. That'd be what? 1/2 delta xp plus 1/2 delta xp, delta xp, just one of them, delta x times p, and then plus 1/2 delta x squared would be 1/4 delta x squared. Okay? Now I'm going to minus. Now I'm going to have to remember to distribute this minus, so I got to keep that in mind. Now I'm going to FOIL this. Well, that's going to be P squared again, but it's going to be a minus. My inners, I'm going to have 1/2 delta xp negative, and a negative 1/2 delta xp. So that's negative 1 delta xp, but I got to distribute the negative. So it'll end up being plus delta xp. And then I got this negative 1/2 delta x squared. That'll be positive 1/4 delta x squared. But then I got to distribute the negative. So it'll be minus 1/4 delta x squared. All right, now some nice things are going to happen in there, I think. The 1/4 delta x squareds cancel, the p squareds cancel, and I just have 2 delta x times p. Now, that's one layer. I want the layer to get infinitely thin. So delta x just becomes a dx, and then I want to do an integral to add them all up. So I end up with integral 2 pi, I'm going to write p of x, because it's going to change. With each layer, p is going to be different, right? How far away the strip is from the center is going to change with each layer. So that's going to be an equation, and then h of x. And h is the height of my strip, which we know how to do height of the strip. We just do top minus bottom, right? That's going to change depending on the region, right? 2 pi can go in front, and then this will just be from A to B, whatever, wherever the strips fill the space. That'll be from A to B. You can pull the 2 pi in front. I usually will when we do these problems. There it is. That's our formula for this new thing. It's a pretty simple formula. But the key then is what is P and what is H. So we're going to write that down. So we go back to this little box I had in my notes here for this idea. So this is layers, or the shell method, however you want to think about it. Okay? And it only works for these revolving type solids because we're wrapping the layers around it just like we were slicing it. So it only works on the revolving ones. But the formula is going to be the integral of the 2 pi you can put in front, p of x, h of x, dx. Now the p and the h, now they could be p of y and d of y depending which way the strips are laying. But the strips are always parallel. If you want to write that in, I know the strips here will be parallel to the axis of revolution, as opposed to with slices, they're perpendicular to the axis of revolution. But I think it's important that we write this in here what P is. P is from the center to the strip. Now that's the one we're going to have to spend a little time talking about. It's really easy once you get the hang of it, but until you get the hang of it, people seem to get confused by it. H is the same thing we've always been doing. H is just the length of the strip. So that's your regular old top minus bottom, right minus left stuff that it's always been. It's the length of the strip. Okay? But P, this P thing we're going to have to think about. From the center to the strip. All right. So, let's go back to that problem we were just doing. Okay? So we got slicing. So the left-hand side is slicing. So what kind of slices can you have? 5 different types of slices. Volumes of revolution, they either have to be circles or washers. If they're on a base, they can be these. If we have a revolving problem, instead of doing circles or washers, we can do this layers method. Okay? Which is this. So, back to the problem we were just doing. Now, so instead of doing it here, so here's our axis of revolution right here. So our strips had to be perpendicular, slices. There was empty space, so we had to do washers. We actually had to divide it into 2 parts. Which way are our strips going to go here? Axis of revolution is vertical, so our strip, and it turns out we don't even have to divide it up into more than 2 parts, do we? Because every strip in there is going to touch the parabola on top and the x-axis on the bottom. So what do we got? We got a vertical axis of revolution. So we got layers wrapping around this way. Now here's the other interesting thing. I didn't even think about this. When we were doing slices, we had 2 kinds. We had the ones for empty space, the washers, and then the ones with no empty space. With shell, we didn't talk about empty space. Does it matter? Well, it turns out it doesn't. You'll see here in a minute. Right. So yeah, it's going to depend on that. So, here we go. So imagine we're wrapping this around. Well, we need 2 things. We need P and we need H. Well, H is easy. Let's do that one. That's what we're used to do. So top Y value is what? Square root of x. There it is right there. Y equals square root of x. So it's the parabola. Square root of x minus 0. Top Y value minus bottom Y value. So that's our H. But what's P? Okay. Kelsey's on to it. What did we say P was? The distance from the center to the strip. Now, right now, it looks like the strip's at about 2.8. I just happened to draw it there. How far is that from the strip? From the center. So, I'm sorry, from the center. If it's at 2.8 right now, how far is it from there? 2.2? How do you get that? 5 minus 2.8. 5 minus 2.8, right? 2.2. What if the strip was here at 1? 5 minus 1. 5 minus x. It's just 5 minus x. It's because wherever you draw that strip, it's at a certain x location. So if it's at 1, 5 minus 1. If it's at 2, 5 minus 2. If it's at 3, it's 5 minus 3. So what I like to do when I draw in these strips, when I'm doing the shell method, is if I have vertical strips, I just label it x. because that's what it is. It's got some x coordinate that it's setting on. So the distance, it's kind of like you could do another strip. You could draw a strip from there to there and just say it's right minus left. It's this x coordinate, 5, minus the strip's x coordinate, which we don't know. It could be any x. So it's just x. So it's 5 minus x. Now, let me go back to my notes here. So P, that is always going to be true of P. P is always going to be something that looks like 5 minus x, or x minus 3, or 2 plus x, because it could be 2 minus a negative x. Well, it wouldn't be minus a negative x, I guess. It could be x plus 2, because it would be x minus a negative 2. So it could be x plus 2. Or it might be y. It might be 3 minus y. Or it might be y minus 1. Or it might just be y minus 0. P will always look like that. P will not have these other equations in it. Okay? So that's probably the best way to get that through your head on P, is you're not looking for as part of the equation. It always has just x or just y in it. Okay, so here we go. So what's our equation? 2 pi out in front times P times H dx, and the strip fills the space from. Do you see how that takes care of the empty space? It just doesn't include that gap from 4 to 5. The strip just goes from 1 to 4. And if we moved it in a little more and had more empty space, we would still just do that. We would just take care of it by what the region is. The strip fills the space just from 1 to 4. So you don't have to go all the way to the 5. That's why a problem like this is why I've been saying for weeks now, the strip fills the space from, right? It's the region, the solid region is where the strips go. And they go from 1 to 4. Okay, anybody type that in yet?
Same thing.
Same thing. Better be the same thing. 328 pi over 15, but much easier. Didn't have to split it into 2 parts. And once you get the hang of this idea here, okay? So, there will be some in your homework where they're going to, and we're going to do one more to practice here, but in your homework, there's going to be some that say, well, I think all of them say use the shell method. So you may even get one where you say, God, it'd be a lot easier to do a disc or washer, circle or washer, but do the shell for practice. You might even have to split it up into 2. Just like, so sometimes shell's easier, sometimes disc washer's easier. And on the quiz, I'm probably going to let you have your choice. And you can go with whichever one's easier. But right now, for practice, we're going to do shell. All right, let's do this one. Do this one with shell. I'm going to go ahead and do it with the other method, the disc washer, our older method, and then we'll just compare our answers. So everybody try this one. So again, you got the region, and it's revolved about the line y equals 4. Now this is one where it's easy to get the wrong region. That's y equals x squared, right? So it's a regular type parabola. But it's easy to get the wrong region here. Everybody look up here and see if you agree with me on the region. Right? What I've seen from some people is when they draw the line y equals 4 in there, they start shading in this part. Right? And it's not that far. It didn't say it's bounded by the line y equals 4. It's revolved about y equals 4. But it's bounded by y equals x squared, x equals 2, and it's in the first quadrant. Otherwise, if you didn't do this, if you did this up here, it would be unbounded. It would just go forever and ever and ever. Okay? So it's got to be that region right there. So that's another thing you have to be able to do is get the correct region. All right, go ahead and go from there. Anybody get it typed in yet? We got something else? What do you got? That sounds like what I had earlier. Now let's. Now the blue. Ignore the blue for right now. The red. This would have to be a horizontal strip, right? Horizontal strip, because you've got an axis of revolution that's horizontal. You got y equals 4. So the layers, again, like this, right? The layers have to be, your strip has to be parallel because the layers wrap around, like so. So we have to have a horizontal strip. So that's my red strip that you see in there. So what is H? H is always just like we've always done, it's the length of the strip. So it's this x coordinate, which is 2, minus this x coordinate, which we have to solve it for x, which would be square root of y. So it's going to be 2, and I know I didn't probably give all of you enough time in this one, but 2 minus square root of y. That's your H. What is P? It's the distance from the center to the strip. Well, it's 4 minus y. Yeah, if the strip's sitting here at 1, y equals 1, then it's 4 minus 1, which is 3. If it's sitting at 2, it's 4 minus 2. If it's sitting at 3, it's 4 minus 3. The distance from the center to the strip. And so again, I usually just like to label my strip. When I put that strip in there and I'm doing shell method, I just label it as a y, and it's 4 minus y. And I said that's what P always looks like. P always looks like this. 3 minus y, x minus 3, 5 minus x, something like that. Okay? All right. So we put in 4 minus y. We put in 2 minus root y. Doesn't matter what order. And the strips go from 0 to 4. The strips fill the space from 0 to 4. Put that in, you get 224 pi over, what was it, 15? Okay? Yeah, no. But it does seem to come up a fair amount. Now, look at the blue, just for practice. In the blue, we could have done our washer, right? We got our axis of revolution here. We want to do slices. There's going to be empty space. So you're going to have vertical strips. So some people like to do vertical strips, so they keep everything in terms of x's. So here you would want to do washers for vertical strips. Big R, little r. You always go from the center. Big R would be from the center to the outside. Little r from the center to the inside of the region. So big R would be 4 minus 0, top minus bottom. Little r would be 4 minus the y coordinate of the equation, which is x squared. 4 minus x squared. Big R minus little r, the strips would fill the space. The blue strips would fill the space from 0 to 2. And you have a pi out in front. Big R squared minus little r squared, 0 to 2. You type that in, you're going to get the same exact thing. That would be a great example of one that's just about as easy to do either way, right? It's about as easy to do with a washer as it is with shell. Matter of fact, like I said, I've seen some people on the quiz do them both ways just to double check their answers, right? Now, on the homework today, I want you to do just shell. All right, so the homework problems are right there in your LH packet. And that's page 427. And I think most of those are just one problem, so it's not a very long assignment. Oh, number 21, I take it back. 21 has 4 parts. The first 4 all just have 1 part, and then 21 takes revolves. But it does say, I think in 21 it says take your pick. So in the book, They kind of chose, it looks like in the book, they chose the one that would give them vertical strips every time. Okay? So, and again, they do a good job of having the pictures drawn and have things worked out for you. Well, the pictures aren't always drawn, I guess. But, so if you want to come up and check your answers. All right, rest of the time is yours to work on that.